Unit Operation Classroom. Today we are discussing using single step trapezoidal rule. It's important, single step trapezoidal rule. We have to find out the value of this integral here. Okay. My name is Shekhar Bhattacharjee. Uh, for an integral, in general integral of this type, we approximate the area between the x is equal to a, x is equal to b by this single step trapezoidal rule method as this integral here as b minus, so this is b, this is a, b minus a divided by 2 multiplied by the functional value of a plus the functional value of b. Okay. So here, of course, in this integral, so this is a is equal to 0 here. This a is equal to 0 and b is equal to 0.5. So this is 0.5 by 2. And the functional value of a, this is my function fx. This is my function fx. So this is my function. We find that the functional value of a is equal to 1 and function value of b, which is that is 0.5, the value is 4. So this is equal to 1 plus 4 divided by 2. The value we get is equal to 1.25. Now, let us try to understand the theory behind this single step trapezoidal rule. Now, let us try to understand the single step trapezoidal rule here. Let's assume that this is the function fx, and single step trapezoidal rule, we assume this to be like a trapezium. Okay, so something like this. Now, if the function has almost no curvature, if something like this, then this would be almost a very accurate answer. But if there is a curvature, then of course there will be much of difference between this trapezium and the actual area under the curve. What is the area of a trapezium? We know this is half into sum of the parallel sides multiplied by the height. So in this trapezium, this is one parallel side and this is the another parallel side. This height here, this is FA, this of the trapezium. And of course, the difference between the two, that means the height of this trapezium would be equal to different these two. So these two are the parallel sides of the trapezium, and this is the height of the trapezium here, and this is FA and this is FB. So that's why this value is, this is the height here, which is this one right here, height divided by 2, and the sum of the parallel side, this is FA and this is equal to FB. Okay, so basically that's what the equation what we have used here, and we got a value of 1.25. Now let us see if we could use what is the actual value of the area under the curve if we do the analytical integration, which is right here. So this is my function. If we do the analytical integration here, which I have shown, the actual value is equal to 1.67. So 1.67, if this is the curve here, so 1.67 is the actual value of the area under the curve. But if we have assumed the single step trapezoidal rule, this is my trapezium here. This is my trapezium here, and this is the value what we have used. So, so this is my FA, and this is my FB, and this is the height of the trapezium. This is 0.5. So, if we use by the single step trapezoidal rule, this is equal to 1.25. So the area of this trapezium is 1.25. If we do the actual integration, which is the area under the curve, then that's equal to 1.67. So the difference between the two, which is this one right area, that is the actual error which is introduced because of the assumption of the single step trapezoidal rule. So this value is approximately 0.42, and this arises because there is a good curvature of this one. And why we see the curvature, if we take the first derivative and then the second derivative is negative 50, so that would be concave downward. So that's why it's concaving. So that's why this error is introduced here. So anyway, the answer to this problem is actually 1.25. So this area is 1.25, which is the actual if we have done the actual analytic integration, this value of I would have been equal to 1.67. But if we use a single step trapezoidal rule, the area under the curve or the value of the integral has been found to be equal to 1.25. So this is just but an approximation. Okay. Why this approximation use? There is a lot of application of this one because we can use the single step trapezoidal rule for quick and approximate numerical calculations of integrals, which might be, let's say, Levin-Spill plot, which is a very famous one. We can find that the total volumetric discharge from flow rate data, V total, of course, is equal to flow rate in this integral here. And of course, in the RTD problems, we come out with the E curve here regularly. So that can be introduced here. In the drawing operation, we also come across this particular integral. So if we use the single step trapezoidal rule, then we can find an approximate value of this integrals very easily. So finally, the answer is 1.25.